Let's recall what we were proving last time, and let's review the last part of the proof, because I was rushing at that time to finish. Right? The theorem was something like this. Theorem. Suppose that you have a solution of this linear problem Suppose that B is bounded potential, B is real valued, suppose B can be written B1 plus B2 such that the first part have a decay the second part has the negative part of the radial derivatives, negative here, less than C2. It has another decay here, 2 alpha, and B2 supported on this set. If then there exists lambda 0 that depends of this node of this C1, of this C2, and this alpha, such that is the supremum in T of this quantity is finite, you are 0. A P is equal to 4 alpha to 4 minus 2 alpha over 3. Okay? We try to do the proof with B2 equal to 0. If you want to do the proof of B2, you insert that in part of your proof, and this quantity will appear in the commutator. Okay? That's not a bad thing. The key of the matter in some moment was that a sketch of the proof says you write f to be this function. Then f satisfy an equation of this form. Right? Where S is a symmetric, A is skew-symmetric, and you have two propositions and that give you everything, but what is important is that you have this estimate. For a sequence of time that goes to infinity, you have this estimate. Two lambda Q. C lambda is this quantity. Is C lambda 0 is this quantity. Okay. You have So let's see here, the L infinity node of this plus lambda, this by Laplacian of this in L infinity, and this goes with this one. And what you want is to say that this quantity can be absorbed in this part, and you have that this is finite. And here is the number appear. Phi is satisfy the following. Is equal to x to the p for x larger than 1. If 0 at 0 is positive outside 0, is radial, is C4, and is uniformly convex, strictly convex on compact set. Okay. You assume that you have this. Of course, in the moment that you write this, P is not 1. Okay, this is a proof for P more than 1. Because you are saying that you cannot say that you are flat and you are strictly convex. Okay? Okay, then let's try to fix the point. Then how big is this quantity? Well, for x, the proof that this term can be absorbed here, that this one is bigger than this one, goes like this. If x is more than 1, gradient of this, second derivatives of this is like x to the p minus 1. This is like p minus 2. This is like p minus 1. Then this is 4x. So there is some constant there. This is like 3p minus 4, or 1 over x, 4 minus 3p. Okay, this is what you have in front of the square of f. What do you have in front here? Right? Before you write this, you're going to have something like T0, Tj, the step before is b of x, t. Suppose that you have f squared plus lambda by Laplacian of this f squared dx dt. And you have a square here. This is what you have before this part. Where is this coming from? This part is coming because you are using this part of the equation, and you are leaving this as an inhomogeneous part. Where is this part coming from? This is part of the commutator that you don't have control to be positive. Then you are here. Okay, then let's see that you control this and control this. How this one behave? Then this is the fourth derivative of this function if x is more than 1. Then this is x to the power p minus 4. That is equal to x to the power 4 minus p. This one decays faster than this. P is positive. Okay, therefore, this term is better than this one. This one have a lambda. This, okay, this. Did I write the lambdas okay? Yes. Yeah. This have a lambda cube. You are free to take lambda sufficiently large, then you can control this one. What about this one? How is b x squared? By hypothesis is forget about B2 for the moment. This is like 2 alpha. And 2 alpha, if you go here, 2 alpha is equal to 4 minus 3p. Right? Therefore, this part decay exactly like this term, except that you have the lambda in the front that help you to control this part. This is going to be a big constant here, sig1, but you can take this lambda much bigger than that. Then you control everything. Then for x larger than 1, it's clear that this term is less than this one. Is this okay? Okay. Now you're going to say, what happened if you are between epsilon, for any epsilon, and 1? Okay? Okay. Now you have to be careful because this definition only is known here, only that. You cannot use this definition anymore. Then, but what do you know? You are only 0 at 0. As you are only 0 at 0, immediately you are positive. That means that since you have to be smooth and radial, you know that this function is 0 at 0. Right? This is because you are smooth and radial. In the moment that you are, okay, in the moment that you see that you have to be positive, that tells you that phi of r is positive if r is positive. You can see that. And in fact, you have this function has to be increased because this one is convex. This function is convex. Then this is going to be increased. Right? Therefore, you have a control from below. Then let's see what is the control that you have from below. Okay. This one is convex. Then you know that all this quantity is bounded below. Then in this quantity, you have this in this domain. Because you are convex, you have this square. And because you are in this part, far from when the first derivative vanishes, you have this. This depends on epsilon. Is that clear? Your function is like this. Function and the derivative vanishes there, but immediately the first derivative vanishes here, but you are convex. They have to be, the first derivative have to increase. In the moment that you are here in epsilon, then you have a lower bound for this. This is larger than something. Okay. Then, what are you going to do? You're going to say, okay, this gives me a lower bound. Then the good part is this. And the bad part is what? Is the L infinity node of this, the L infinity node of this multiplied by lambda. And the bad is this. This is square. This is the bad. Can you control this with this? Yes. Once that you fix the epsilon, this is a fixed number, and now you take lambda sufficiently large because this will grow like a cube in lambda, and this will grow linearly in lambda. Then you can control the things. Then it remains to prove only what happens close to 0. And now close to 0, you cannot use that because the derivatives at 0 is 0. You cannot have a lower bound close to 0. You are out of this. You have to use this part. And you use the Poincare inequality. You use that this is convex, right? You use Poincaré. How you use that? You say, well, I have the gradient of f, second derivatives of this, dx. This is larger than this. Some constant that depend on phi in the domain, in the unit ball, uniform, in the ball of center 0 and radius 1, f squared dx. And now, if you are in this domain, roughly speaking, you have this inequality. Very roughly speaking, you have this. Because you have to truncate and do it, roughly. You have this. Okay, you have to truncate. We did that with all details. What is that? Let's see, what is the epsilon have to be? Give me 1 second, I have to. Seven. Okay, I need to be sure that I put the epsilon where it is, otherwise I will not get it. Perfect. We have it right. Is this okay? Is this okay? Then what do you want to control? You want to control this part multiplied by this quantity. I mean, you need to control this part, multiply it, roughly speaking, by this. Square plus lambda, this, and infinity. How you go, and what do you have in front of this quantity? Only a lambda. Then you have lambda in both sides. This grows linearly in lambda. You have a lambda here. Right? But what is exactly that you control? You control this. Therefore, you only need an epsilon part of it to control this. Then how you finish the argument? Well, I fix epsilon sufficiently small such that this is true. I fix epsilon sufficiently small that epsilon, right, that this part is less. Now I multiply by epsilon here. This is less than this one multiplied by epsilon. Then there is an epsilon in the front here. You have this lambda. Then I have epsilon here in front of the lambda. That is going to be the bound in this side. And in this side, I don't have that. I have the lambda only. Therefore, you choose epsilon sufficiently small such that you control. And when that you choose epsilon sufficiently small, you choose lambda sufficiently large such that you do divorce. Is this okay? Is that more or less clear? How you do it? Of course, this is not true. You have to truncate these things and so forth, but this is the key of the matter, that you have an epsilon here. Because otherwise, this part grows like lambda, this part grows like lambda. You have to have something small in front of this. And this is Poincaré. When you pass from here to the gradient, you pipe with an epsilon. Okay? Okay. To put this is to put it in there. Okay, then this is the key of the part of the proof. Okay, then the question is, let's go to some remark to see how you remove this and how you construct a function that is like that. Any question? Okay. We have all this. We don't need any of this. Need this. We don't need this. We don't need this. Okay. Let's go here. The theorems say if alpha is 0, that means that the potential is bounded. Then P is exactly 4/3. And the extremal theorem is if alpha were 1/2, that is not true, you need to have 1/2 plus, then you need that P is equal to 0. P is equal to 1. And this is true also. You can prove that. But what do you mean P to 1? I mean, you cannot put P equal to 1 because you need the convexity. Okay, then what do you choose if P is equal to 1? Okay, let's see if I choose. All this is nonsense. All this is this. Okay, this one. Okay. If P is equal to 1, you have the problem that you cannot grow linearly. Then you do this trick. You choose your function to be this one. Phi of r is going to be, I don't know, 3r minus the integral between 1 and r, dr 1 plus the log of r, if r is more than 1. Therefore, the derivative with respect to r is 3 minus 1 over 1 plus the log of r. The second derivative of this is 1 over r, 1 plus the log of r squared. And see that you have convexity. This is positive. If you choose, suppose that the first try will be to say, okay, I cannot choose this one. What about if I choose this one? You see that this doesn't obey the law that when you take derivative, you lose 1 power. In some moment, you lose 2 powers. You have to do the computation. Then that doesn't work. Then you subtract this. And of course, you have to arrange things such that this function can be extended to be C4, can be extended to be 0 at 0, positive anywhere besides 0, strictly convex, and so forth. But that's not it. Then you do this. And you see that you don't have something so nice. This is what you would like to. You say, well, I grow here linearly. I am a constant, and I am 1 over r. Right? This is almost true, but you have an error coming from a log. If you put r here, you will have 0 here, and it doesn't work. Okay. Okay, how you match this to be complete? Okay, you have the function defined. This is the radius, and you have the function defined here, and you want to match this somewhere like this. Well, it's a boring computation. There is many ways to do it. Is that you say, well, I want to define for x less or equal to 1, I'm going to define phi of x, phi of r, equal to some constant a2 r squared, a4 r4, a6 r6, a8 r8. There are better ways to do it, okay? Then I'm going to define this in this way. It's a polynomial that is even. Therefore, in the moment that you are even, you are smooth at 0. Then you want to match the value for x larger than 1. Then what is the value in 1? Accordingly to phi of x is phi of r is r to the p. Then you match these two values, phi of 1 from the right, from the left, the derivatives, right, up to 4. You have 4 conditions here. Then you have really 4 conditions because you have 4 derivatives, but you really have 5 because you have this one. Then you have 5 conditions, but you have 5 choice here. However, you still need, now that you've solved this, is that this function is convex. Then you compute since, and you see that the third derivative of this function doesn't vanish. It's always positive. And the second derivative at 0 is positive. Then you have that this is strictly convex. Then it's a boring computation, but you have it. Okay? For both of that. Then you can, this kind of function exists. You can do it better in other ways, but I don't want to. This is a explicit computation. Then this kind of thing exists. And of course, you're going to complain. You are putting this function here. You are not putting exactly this one. Well, but this function like this is in L2. Everything that happened for x less than 1 is okay. This function u is in L2. This is real. Then you can't. The only important thing is what happened at infinity. Okay. Another remark. Is this. Remark. Where do we use that this is real valued in our proof? We always put absolute value. The only moment that we use that the potential was real valued is that you preserve the L2 norm. It was the only moment. If you go back to the proof, the only moment that you use this was when it is real valued, because we put it in the homogeneous part and we put absolute value all the time. We never use that this. The only moment that we use that this is real value is to say that you preserve the L2. Okay. Now, suppose that you have this elliptic problem. Laplacian of W plus some potential that depend only of x, W equal to lambda of W. W is an H1 function in Rn. Suppose that lambda is real. And suppose that the B is complex valued. You have this eigenvalue problem. Then, if you solve this function solve this problem. When you take derivative with respect to t, you pick up I lambda, and this is where you have the other. Then, if W solve this function solve this problem. So it's very simple computation. The derivative with respect to t of u is I lambda, the exponential W. And then when you apply this operator, multiply by I, this is exactly equal to I. You're going to apply it here. This is exponential Laplacian of W plus B of W. Then you cancel the exponential everywhere and the I everywhere, and you have this equation. Is that okay? And now look at this equation. Okay, this is not real valued, but the L2 of this is preserved. What is the L2 of this? The L2 of this has nothing to do with the time, because in the moment that you put the absolute value, this disappears. This is exactly equal to this. You're assuming that you are in H1, you are okay. Therefore, you can apply the theorem here. And what does the theorem say? Is this potential you can apply this to the theorem. If the potential is bounded, let's see that is in L infinity. That is the case if alpha is 0. And this integral is finite. When you put absolute value, there is no x there. You don't have to put supremo in time because there is no time there when you put absolute value. If this is this for p equal to 4/3, for lambda, so very large, that implies that W is 0. And this is Meshkov result. Okay, you're going to complain that you have a lambda here, right? You have this. Okay. You can remove any condition over lambda except to be real. You need this lambda to be real to see that this absolute value is 1. The absolute value of this quantity is 1. How you remove the lambda? Well, you write lambda W, lambda, something that lives close to 0. I mean, this is a smooth function that is like this. And lambda outside this. This is going to be your B2. That is there. This is going to be part of your B1. Therefore, you don't need to have any condition here on B1 because the condition on B1 is that you decay, and this has compact support. The condition of B2 is that the radial derivatives of this have some decay. The radial derivatives of this is 0 because this function is 1. Then you can apply the theorem. It doesn't matter what is the radial decay that you put here. It doesn't matter if you put 2 or any another number. Then you have proof that you have this theorem. If you solve this elliptic problem with the complex potential and this lambda real, and you have decay that is more than 4/3, then you have to be 0. 4/3 is sharp. Meshkov gave an example that you have potential that are complex values that you have solution that decay exactly like power 4/3. The result should be that if B is real, this P should be 1 plus epsilon. And this is an open question. Okay? Huh? Oh, yes, I'm sorry. Okay, this is, let's put theta here. Theta, thank you. This is theta, thank you. Okay, and then this is theta. I mean, the lambda doesn't have to be anything with the psi. It has to do, okay. Theta, okay. And this lambda has to do with theta is the eigenvalue. Okay. Let me give an application of this result to a nonlinear problem. That will be very interesting that you can get anything below 4/3 if this potential is real. From what?
For uterine force.
Well, yes, because you can take the Meshkov result, but of course now you are cheating because you are not putting real value. If I change this and I put the L2 node of this is preserved, it's sharp because you have this example. Okay, but if you put real value, I don't know. Okay, let's try to see if we can get an application of this result to a nonlinear problem. Suppose that we consider this quasi-linear Schrödinger equation. A is a positive number. This is nonlinear. You are in Rn. You have the semilinear Schrodinger equation. Suppose that you solve this equation. Then you have that u sigma of x t equal to sigma to the power 2 over a u of sigma x sigma squared t satisfy the same equation. Why? Okay, when you take derivatives with respect to t, how many powers of sigma you have? It gives you 2 over a plus 2, because your derivative is in t. When you take two derivatives in x, what do you have? 2 over a plus 2. When you take power a plus 1 of this quantity, what do you have? 2 over a plus 1. That gives you exactly 2 plus 2 over a. Then all the powers are the same. Okay? This is for any sigma positive. Okay. Then what you are doing here is to say, well, if this function u is defined in some interval, this function will be defined in an interval that change accordingly to this rule. I mean, I just move this. What is the psi of the initial data? What is the psi, the derivative with respect to s of the initial data here in L2? Well, by homogeneity, if you take derivatives of this, you have this power coming of psi. You have taking s derivatives, this will come out as s. And since you are taking the L2 norm, you have to switch chain variable, and it's going to give you this. And you're going to have the derivatives of s of u of x0. Something that doesn't depend of sigma. Then if you take derivatives of the initial data, that when you do this transformation, you will get this quantity. What you want is this quantity, this power to be 0. Why do you want that? Because then the data, the size of the data in this norm doesn't change when you do this transformation. And this is called you are in the critical space. Then you don't, therefore, you have to say that s is equal to n over 2 minus 2 over a. Then this is the critical with respect to the power a. That tells you that by doing this transformation, you don't change the norm of this quantity. Therefore, if you don't change the norm of this quantity, by doing this transformation, if the time of existence depends on the size of the data in this norm, you are not changing the size. Doing this transformation, you will have global solution, because you can change this whenever you want and extend the business. Then this is critical in the sense, for example, if you are in L2, suppose that you want the critical to be L2, this quantity to be 0. You need that A is equal to 4 over n. Is that 4 over n? Right? Then I want this quantity to be 0. You need that A to be equal to 4 over n. For example, critical in L2. If you want to be critical in H1, that means that you want S to be 1, then S sub A, this quantity is 1, is equal to n over 2 minus 2 over A, then you need that A, 2 over A is equal to n2 minus 1, that is n minus 2 over 2. then A is going to be 4 over n minus 2. And you only can do this for n larger than 3. This is the critical power. And what is the theorem that you have in these cases? The local existence theorem forget that A can be a fraction and then the fractional derivatives of a fraction is a pain, but suppose that we don't get into this technicality theorem. In this space, homogeneous SA of Rn, that the norm here is exactly the norm of this. This is the norm. Then you have a theorem that says for every data that is here, this is more or less true. For certainly in L2 is true, in H1 is true. There exists a time that depends on who is the data, not what is the size of the data. It's a huge difference. If that will depend on the size, by this trick you will make it global, and you will see that you cannot make it global. There exists a time that depends on who is the data, and there exists a unique solution U that defines a continuous curve in H homogeneous in this space, intersection, other thing here that has to do with something called Stricker estimate. We don't go there deep. The question is this global? Well, the answer is no. In general, is no. Then it comes out that it's much. If you want to do something not global, you put the plus here. Take the plus sign, and the plus sign is called focusing case. Okay. And now do the following. Take SA to be 0. That means that you take the nonlinearity A to be 4 over n. You are critical in L2 to make your life simple. Okay? And look for a solution. Look for solution of the 4 exponential of IT phi of x of this. Okay, now we are in this equation. We are trying to get the plus sign, the power 4 over m, because we want something in L2. Then if you insert this there in the equation, you're going to have that the derivative with respect to t. Okay, let's write this. Derivative with respect to t is going to give you an I, but you already have an I that gives you minus, right? Phi. Exponential is going to be common everywhere. It's going to disappear. It's equal to the Laplacian of phi plus phi absolute value A phi. Then the only thing that you require for this to be a solution of the equation is that you solve this. Is that correct? But suppose that you consider something like this. And A is 4 over n. Something like that. Okay. Then the elliptic theory and result of Berestiki, Lyons, and Strauss say there exists unique positive solution of this problem. And the moment that you are positive, you don't care if you put the absolute value or not. And this solution is radial. And this solution at infinity behaves like this. Decay exponentially. Okay? If that bothers you, take n equal to 2, and then you have an integer power that is not so complicated to work with. Okay. We are trying to get something that is global, and the answer is no, but we are not getting anywhere yet there. There is another trick in all this. It says the following. If this is the conformal transformation, and maybe the first people who wrote that was Ginevra and Bello. The conformal transformation says the following. If you solve this equation, then let's take this one because I don't want to miss the Greek letters. B of x and t equal to exponential of I w x squared for wt sigma wt to the power n over 2 u of x mu wt t. This is like this, eta, theta t, sigma, solve this equation. Put A. If this equation is this function, you solve this one, you do this transformation with this parameter. You have 4 parameters. You have the parameter W, you have the parameter mu, you have the parameter this, and you have the parameter theta. All these are real, and the only condition that you need is that you certainly need a condition. What is the condition that you need? There is a product that has to be equal to 1. This one. Okay? Okay, it's a long computation if you want to prove it, but you can take it as a fact for the moment. If this is a solution, this new function is also a solution. In particular, if this quantity is 1, you will get the same equation. In particular, if this quantity is 1, if is 0, you don't have this part and you have the same equation. That means if A is equal to 4 over n, that means that you are in the critical L2 case, critical L2, the same equation. When you are in the L2 critical case, that this power is 4 over n, if this solves the equation, you do this transformation, you solve the same equation. Okay, now we have everything that we need. We have this solution. We have found a solution of our problem. In the moment that we find a solution of our problem, we can do this scaling argument and find other solution, or we can use this transformation and find other solution. In particular, you have that doing this transformation, right, with, let's see if I put the parameters. If you choose the parameter, choose U to be this one, as in here. Choose the parameter to be this one, mu theta W equal to 1, this one equal to 0. Therefore, you have that this is a solution. W. Okay. One second. I send 1 second because I copied wrong the transformation. I want to copy this. Okay. I think. Okay, I want this transformation. You will help me to say how do I have to choose the constant. Okay. The t is going to be this one. 1 minus t. The exponential is going to be e to the I. W is going to be minus 1. Then this is going to be 4, 1 minus t. Then maybe this is not correct. I have to choose that. Then this is 1 minus t to the power n over 2. And you have this one is x 1 minus t. Okay. To do that, we have to choose what? W has to be 1, or minus 1, because we have that. This has to be 1. W is minus 1. We have these 2. This is 1. This is minus 1. This is 1, 1, minus 1. And we don't care too much which other one we have to choose. We have to obey this law. There is not, this function doesn't depend on time. Therefore, we have to obey that. We can choose theta equal to 1. And this sigma, this number equal to 0. Okay, we choose this. Then this is a solution of, if you wish, this same equation. Okay? Suppose that A is equal to 4 over n to simplify your life. Then this solves the same equation. Solves this, the equation, this one. dt u b I equal to Laplacian of b plus v to the power 4 over n b. It solves exactly the same equation. Okay, let's simplify our life. Question, where this solution live? Okay, this is a number. Okay? What happened with the absolute value of this? If you compute the L2 norm of this, you have a constant, independent of time. This is you are going to change variable to compute the L2. However, if you compute the derivatives of this, when t tends to 1, this goes to infinity. Why? Because if you take derivative with respect to x, well, you have some derivative here, but when the derivative hit here, you are going to have more powers of 1 over t. And that gives you, when you do the chain of variables, you have too many power of 1 over t. Then what is the graph of this? Forget all this. What is the graph of this when t goes to 1? It's concentrating like this. Then what you are saying is this. Okay, I remove a piece of the theorem, but in fact, the limit when t goes to 1 of this quantity, the absolute value of this, it takes to the delta, some constant of the delta in the distribution sense, whenever that means. Okay? Therefore, you see that you can have, for t equal to 0, you get this some nice data, that is this function that is infinity. Well, it's a solution of radial. It's a nice function. It's in H1. If this constant, if this number here is an integer, it will be infinity, right? But you have blow up. You have that the solution doesn't exist. Why the solution doesn't exist? But the solution concentrates accordingly to this profile. This part is not going to bother you too much. It's oscillation. When you put absolute value, get this. This is the chain of variable in L2. And the concentration that you have is of this form. Okay, this is one that how the blow up occur is going to occur of this in this fashion. Right? The question is, can the blow up occur faster than this? You have proved that you have some blow up result or some that the solution cannot go beyond. The solution here exists for t positive, that we are working only for t positive up to 1. Okay? And you have proved that you have explicit way to see that the solution can be not continuous after t equal to 1 because it concentrates in this way. Okay, the question is, okay, now that you know that the blow-up occurs, you know that it occurs this way because everything is explicit. You know exactly the solution. You know this is equal to this. You know puts absolute value and so forth. But there are many ways that you can put that the blow-up occurs, and you don't know anything so explicit. I mean, you know that this is one example that the blow-up occurs in the critical case, but there are many other examples. Can you concentrate faster than this? For example, can this be this number huge, any number that you wish? Can you concentrate like the Gaussian? Okay, let's see that this is not the case. Okay, let me write the theorem. Okay. Theorem. Let's see if we can write the theorem. Suppose that U continues in 0, 1 in the critical power SA of Rn solution of your equation dt of U equal to Laplacian of U plus U to the power AU. You know that SA is equal to N over 2 minus A over 2 over A. Let's do it like this because it's going to be easier to do it like this. Suppose that there exists a function Q such that the solution that you have blow up in this way. What are you saying that you have this? Who is in the case, in our case? Let's see that this is not so crazy. In our case, what is the point? In our case was The one is A is equal to 4 over n. Therefore, this quantity that you have here, 2 over A, is n over 2. And the phi that controls the business is this Q that you have here, is the one that is given by the elliptic theory that decay like this. Okay? Then we are extending that. Suppose that you have Q such that Q satisfies then U is 0. You cannot have a blow up that concentrates too fast here. This number here that you have to be controlled. Maybe I should put C1 and C2 here. In other words, this concentration that you have explicit is the faster that you can have. You cannot have anything Gaussian, anything power more than 1, anything arbitrarily there. Okay, how we prove this theorem? Okay, how do we prove this theorem? I think that this will be enough space. Okay. You have a solution of this equation with this power. Then you do the conformal transformation. Proof. Use the conformal transformation with I think that this is correct, this 0. Therefore, you have that u b of xt, let me write b like this, equal to 1 plus t n over 2 exponential of I x squared for 1 plus t u of x 1 plus t, t 1 plus t solution. Of what equation? Well, now it is not the same equation because we want something general of this one. Or satisfy this equation. Okay, that's what we say. If we apply this transformation, we have that, and we apply this transformation with this parameter, we have this. Okay, then where is the solution? This solution is defined. Where is the B defined? The original U was defined in the interval -1, 1, if you wish. It's blowing up at the time 1, right? It's blowing up at the time 1. But where is this function defined? This never reached the value 1, where you have a problem. It reached the value 1 at infinity. Then this is defined in the interval 0 infinity, if you wish. Okay. Okay. How big is this function? B of xt is equal, if you put absolute value, you kill the exponential that bother you there. You have equal to n over 2 b of x 1 plus t, t plus 1 plus t. According to your definition, this hypothesis is that, I'm sorry, this is u. This is u, okay? U is controlled by this, in this form. The blob of u is controlled by q with this. Why this number? This is a number that you need to be sure that you preserve the norm of this. Okay, this number. Okay, if you were critical L2, it will be n over 2. Therefore, you have this quantity, 1 over 1 plus t, n over 2, 1 over 1 minus t, 1 plus t to the power 2 over a, because this is what you have. Your time is this one. And then you have q of what? Q of x over 1 minus t. But who is x? X is this variable, and t is this variable. X is this variable, and t is 1 minus t. That means it's 1 minus this. Is this okay? Okay. Then this is equal. If the computations are correct, okay. What happened here? This is going to be like x, 1 plus t, divided by 1 plus t, divided at 1 plus t minus 1. This is t. Right? Yes, this is a t here, right? Okay, thank you. Otherwise, then the computation will be, this is 1 here. Therefore, all this is x over x only. Then all this is, and this one is 1 minus t, 1, this is 1 over 1 plus t, all this, 2 over a. Therefore, all this will be equal to 1 over 1 plus t n over 2 minus 2 over a q of x. Then this function b is controlled this way. Okay. Now, how big is the potential? How big is this potential? This is your potential now. You have the solution. You have all the right to call this b of xt. It's real, and so forth. Then how big is your potential? B of xt is equal to this 1 plus t to the power a n over 2 minus 2, b to the power a, b is this, to the power a, all this, right? B of x on t to the power a. And that is equal to 1 plus t a n over 2 minus 2. This power a of this is power a of this is going to give you 1 over 1 plus t. Power a of that is going to give you a n over 2 minus 2 q of a of x. You take power of n. Because these two cancels, and this is q of a of x. Or you want like this. Whenever you want to write it like this or the other way around, doesn't make any difference. Now you have a potential. What do you know about this potential? This is your potential. What do you know about this function q that decay like this? Then this function q decay like c exponential of power a of this. This is c1 to the a minus c1 to a to the x. Okay? It decays like this. And what does our linear theorem say? If you solve this problem with this potential, and this potential is bounded, right? If this potential decay, what was the theorem? What was our theorem that I raised there? What was our linear theorem? Our linear theorem says you have a global solution of this source and b of xt decay like 1 over plus 1 x squared alpha over 2 with alpha more than 1/2, strictly more than 1/2, and it's bounded. L infinity, real valued. You cannot decay more than linearly arbitrarily. Then what happened with this guy when your potential? Well, your potential is decaying. I mean, forget about that you are asking for a polynomial decay. It's decay exponentially. Then you have it. Then you cannot decay like this because you have this restriction. If you have this restriction, then you know that you cannot decay arbitrarily with this. This cannot be arbitrarily. Some moment, if you surpass some value, this is 0. Then this is, by our linear theorem, if A over C2 is larger than lambda 0, then everything is 0. Then B is 0, U is 0. Then you cannot have a solution that concentrates faster than the one given by the ground state or the standing wave. Is this okay? There is another application of this, but I think that this is, good enough to see that, I mean, all these problems, even that are linear, you can apply to things that are not linear once that you know that the solution exists. Right? I mean, it's a kind of a tricky, simple trick. Okay. Any question, because we completely switch to another equation? No question? Okay, by the way, the explicit way that we construct this solution is, I only know that work in L2. I don't know if that works in other things. Then the theorem is more general because you don't know if the blow-up occurs in this critical space. In L2 is none. I don't know explicit thing that you have blow-up in here. And you can check that this has to be the only constant. I am putting here, I'm not assuming that the solution is in L2. Okay? Okay. Let's say what we are going to do in our last class. There has been a lot of work in nonlinear evolution equation, dispersive or hyperbolic, to deduce what is the minimal regularity that you need in order for this problem to be well posed whenever there's some definition of well posedness, right? I mean, people have, I think that maybe Ginevra and Bello, Casanova and Weisler, Kato were the first people who worked on that. And if you read a paper by Kato, when he proved that the KdV is well posed in 3/2, he finished the proof and he complained. He said, well, after you read the proof, you are not using the third derivative as anything. You can put 3 derivatives, 5 derivatives, anything. The only thing that you are using is that the 3 derivatives is an skew symmetric operator. When you integrate by part, disappear. And then he complained that he would like to have a proof that use the linear part. What he's saying is, if you have this result for the KdV, right? And you ask for the initial data to be in the subvariate space 3/2 plus R. Well, then this proof will work for this or without this. The only thing that you are using is that when you are in this space, by subvariate, you are in sig1. And when that you are in sig1, this is well defined and so forth. Okay, then he complained. Then it has been a huge development in this direction, and what you can see is that we are not doing any of this. We are asking a simple question: what is the best possible decay that a solution of the dispersive equation can have? Very simple. I mean, even for the Schrödinger equation, this is, if somebody asks you what is the best decay that you can have in the fix an interval t and ask what is the best decay in a space, is the one that we just construct. That is, this is the solution of this form, where this satisfies some nonlinear problem of this sort, and this decay exponentially linear. This is the best known. Is that sharp? Doesn't know. Can you construct a solution of any? Make it simple. This. Can you construct a solution of that for short time decay faster than exponential? That is not clear. Okay, then it's for the KdV, this is known. For the Schrödinger, for a strange reason, it's unknown. Or if you wish, the problem is, for the KdV, there is a part of the fundamental solution that oscillates, and there is a part that decays exponentially. Using that you decay exponentially, you can construct things that make you the sharp scene. The problem with the fundamental solution of the Schrödinger is that you don't decay at all. It's only oscillation. Things make it more complicated. Okay. What we are going to work now is with an equation that have nothing, it has decay, but nothing can be exponential. It's much restricted. Okay, and it's called the Benjaminon equation. And you will see why do we cover some of the correct. Was afraid that I didn't write the equation. Okay. This is H is the Hilbert transform that we study in the first week. That H of F is minus I, the sine of C, this go back. Okay. And we are going to study this, the initial value problem. You have this, and you prescribe the initial data. and you put that in a Sobolev space, and this Sobolev space, everyone know the definition of the Sobolev space? Yeah? Okay. Then the question is, how low can you go and have local well-postness? Okay, let's see local well-postness. And then we will compare with global and so forth. Okay, it came out that Kato, Abdeloua, Bona, Phelan, and so prove that you need S larger than 3/2 at, okay. If you have more than 3/2, it's okay. But this is exactly the complaint that Kato have, that 3/2 is only using that this is skew symmetric. That when you integrate by part, the only thing that you are using is this, or Hilbert transform, it doesn't matter the commute. You are only using this. For real solution, this is 0. Then I think you also proved 3/2 and Kato proved 3/2. Okay. Then later, I don't know, I proved exactly that you can reach 3/2. Right? Okay. And what is the big point? There was not too much big point to say this. The only thing is that instead of the only thing that you need to control to be in a good shape is this. You need to control the L infinity norm of this in a space and the L2 in time. This is what you need to control. If you use Sobolev, you say to control the L infinity of one derivative, 3/2 will be enough. 3/2 plus. 3/2 exactly is not. But if you use a Strika, you can reach that and you reach that point. Okay, we came out that Koch and Setkov prove that S more than 5/4 is enough. And the idea is that you really control this, and you do something more sophisticated than a Stricker estimate. Then Koenig and Koenig proved that S9/A was okay. You need to do something like this. Of course, the sequence has to be decreasing because you cannot go and prove something weaker. Then tau proves that S equal to 1 is okay, and that is nice because, the conservation law in the Benjamin Ono appear in L2, H1/2, H1, H3/2, and so forth. They jump in 1/2. Then tau proved this, but the proof have nothing to do with this. It has to do with a chain of variables using a gauge transformation that I understood reading the paper of Molinet and Didier. I finally understood. I couldn't understand that from the original one, right? I understood that there. Okay, it came out that you can refine his argument, and Planchon and Burke prove that 1/4 is enough to prove that. And then Ionesco and Koenig prove S larger or equal to 0. But then when you reach so low, you have to be careful what you mean, where is the uniqueness hold, and so forth, right? Then in the paper that I refer by later, Molinier and Pilot improve the uniqueness here and explain in a very nice way how this argument works. I recommend that paper. Okay, we are not going to go below, we are going to have completely the opposite. We want to go how high you can go in a different direction. Okay? Then, in the same way, when you have the Schrödinger equation, this is the operator that you have in the Schrödinger. This commute with this operation. Hopefully, I mean, this commute with this. The KdV is this one. It commute with this. And the Benjamin Ono, the linear part is this. It commute with this. Therefore, this commutator relation tells you the following. If you want to preserve one power, you need one derivative. You want to put it in L2, very roughly speaking. For the KdV, if you want to preserve one power, you need two derivatives. And you can preserve that this is very sharp. There is no way that you're going to preserve decay if you don't have regularity. And for the Benjamin Ono, if you want to preserve one power in L2, you have to have one derivative. Remember that the Hilbert transform is like derivatives of order 0. Okay? Then when this idea that you need at least the same amount of regularity can be preserved, you don't have a problem. If you put weight, then to preserve the weight, you need regularity. Okay? Then with this in mind, Rafael Llorio proved the following. Okay, define this space S, R, HS of R, intersection L2 of X, R, dx. And let me allow to, 2R. Let me put 2R here and R there. Remember that you want X 2t dx Hilbert transform. Then if you want this commute with the linear part, you want this to be in L2, then you need, for this part, you need H1. Therefore, x by u will be in L2. Then you need that u will be in L2 with x squared. Then you need one derivative to put 2 power here. You need 2 derivatives, you put power 4 here, and so forth. That's the relation then. Llorio proved the following theorem. If the initial data is in 1, let's say 2, regularity 2, and R equal to 1 or 2, then you have local well-posedness in this space. That means that there exists time that depend on the norm in this space, and there exists a unique solution that is a continuous curve in this space, and so forth. Then 2 is okay. If you have 2 degrees of regularity, you can preserve or to what you expect here, 2 degrees of power. Okay, the power will be 4 because we are writing this way, but remember that. Okay. Then he proved that if you want to preserve 3, you go like this and you say, well, suppose that you are in 3, 3. Okay, I put in 3, 3 means that I want power 3 here and 3 derivatives, but since this is in L2, I have to, it's like putting 6 here. Okay, it's a matter of notation. Then you need this. If you have mean value 0, then you have local well-posedness in this space. That means that this C33 intersection with the data that has mean value 0. Okay. And this is preserved by the flow. Everything is real valued. This is preserved by the flow. Then you have a solution that starts there, he proves that you stay there. And then he proved, the third one is, suppose that U is a solution that for short times, there exists a time such that the solution is in 4-4, intersection any other space that you want. Then you are wasting your time because your solution is 0. There is no possible solution to preserve 4 decays. You cannot decay, you cannot have this 4 here. Of course, your regularity, you can have it, but you cannot claim that X, this is 4, this is 4, this is 4, this is 8 here. You cannot have this. The solution is in L2. You cannot have this for T in an interval. The solution cannot decay at all. Okay? Okay, this was surprise, but then you go back and you say, okay, all these solutions, there is a cubic Schrodinger equation that can be solved by inverse scattering. There is a KdV that can solve the inverse scattering. This one formally can solve by the inverse scattering. How the Benjamin Ono have traveling wave solution. The traveling wave solution is that you have solution of this source where this phi is something like almost is something of this sort. The traveling wave, if you remember, the traveling wave for the KdV is a hyperbolic secant that have exponential decay. The one that we just did for the Schrodinger equation, it have exponential decay. Linear, but exponential decay. This one have a polynomial decay. Okay? Then, in fact, has written, I think it's that one. But I don't know. Let me check if the constant is okay. Yeah, it's okay. Okay. Then you see, well, since it have to decay cannot decay very strongly here. Then Raphael improved his result, this one. Then Theorem, also Iorio, proved this result. If, suppose that you have a solution that you know that there exists. It's a C3 with this business. Suppose U is a solution that you know that exists. It's in C3, 3 with mean value 0. It's a solution. Suppose even that U is C4. It's in H4. Let's say if, let me write it like this. If U sub 0 is belong to 3, 3, mean value 0, intersection H4, but what Raphael proved is that you have this. You have the regularity 4, you have the decay 3, you have mean value 0. Then there exists a unique solution here. If you have 3 times such that at these 3 times you belong to 4, 4, you are 0. If there is 3 times that if you are at 3 times when you belong to that 4, 4, you are 0. Then it's forbidden. Of course, you can prescribe your data with compact support. You have a freedom to choose one. What is not clear is that you have it for 2 times. This is, complicated issue is, right? Why this is a complicated issue? I mean, to pass, you just say this result should be 2 times. You can prescribe one data, anything you want, compact support, but you should not. But this, then after that you try to prove 2 times, you start to convince that it's very complicated to have 2 times. Why? Well, because if you go to the Schrödinger equation or the KdV equation, the way that you prove any of these 2 local existence is using the contraction principle. You use contraction principle. And for the KdV or Schrödinger equation, you do contraction principle. What is the contraction principle? It's that you use the integral equation and you use estimate or Burgen space or Stricker or smoothing effect or anything. But what does that tell you? That once that you cross on S, magic X that is the best possible, then the nonlinear part is as good as the linear part. Below that S, the nonlinear part may not make sense or something like that. Well, it came out that Setkov, that Molinier, Setkov, and so prove that doesn't matter what is the S that you choose as large as you want, you cannot use contraction principle in the way. There is no way that when you write this an integral equation, you can say, oh, the nonlinear part is as good as the linear part. It's never happened. Then you have, when you write the integral equation for the Benjamin Ono, this is the group, you have to be very concerned that you cannot say that one piece is better than the other. Most of the time, if you were in the KdV and you are above this, you're going to say, oh, this part is better than this. For a strange reason, the nonlinear part is better than this part. In here, you don't have that. Then you can have cancellation. This can be at the same level. You don't have any of this. Then the 3 times start to play a role when you know that you cannot say, okay, I cannot put the weight, but maybe I cannot put the weight in both, but this doesn't compensate that this part and this part cancel and you put something. It starts to be complicated. Okay. Well, then I will stop in a minute, but what we were going to prove is the following. This is Raphael Resol. He said that 1 is okay, 2 is okay, 3 you need mean value 0, and 4 forbidden. Okay, you need this. Then suppose that you want to work with fractional power. How far can you go? Then in what moment, this is forbidden, this has to have mean value 0, this is okay. Then how far you can go with okay, how far you can go with mean value 0, how far is forbidden. We will do that next time. I will not tell you which is the statement. So that you will come to the next day. Okay, then what we are going to do is that somewhere in between there is some magic number, and we are going to prove that if you are there, if the interval is open, you are okay. If the interval is closed, you are out. Okay, this is completely resolved. Okay.